Dr. Ashwini Kumar Rathore is working as professor in chemical engineering at HBTU Kanpur. He did his BE from GEC Raipur in 1997, followed by MTech at HBTI in 1999 and PhD from Manit Bhopal in 2003. He has published 24 of papers in national and international journals. His research area is reactive extraction waste management. Thank you so much, sir, for your presence. Now I request Mr. Vikas Vishwakarma, sir, to felicitate Dr. Ashwini Rathore, sir, with a sapling. Thank you, sir. For the first presentation, I call Mr. Kudzai Hamish Ruzvidzo for his presentation.
Namaskar. My name is Kudzai Hamish Ruzvidzo. I'm from the Delhi Technological University, and I'm here to present on my presentation titled Exploring Novel Organic Draw Solutions for Forward Osmosis Desalination, Performance Regeneration, and Modeling. Now, the objective of the presentation, the first one, I'm going to analyze and give a report on the novel binary draw solution. The second one, I'm going to discuss its properties. The third one, I'm going to compare experimental and modeled results. And lastly, I'm going to talk about the regeneration potential of the draw solutions. Now, first of all, the world population is growing, with India surpassing China to become the most populous country in the world. Now, the word desalination, the word D means remove. So desalination is a process in which dissolved salts are removed in water. And as you can see from this diagram, about 96.5% of the world available water is in the seas, which has got high salinity. We cannot use them. Then about 1.74 is frozen as ice and others. So nearly 97.5% of the available water, we cannot use them for human consumption, but the world population is increasing. This is the importance of seawater. This is Africa, where I'm from. This is India. This is the Middle East. These are countries. And according to the West Bengal governor, KJ Nath, in 2017, he projected that by next year, nearly 1.8 billion people will be living in areas with high or absolute water scarcity. I'm from Zimbabwe. Right now, my country is facing cholera outbreak caused by unsafe drinking water, because we use the chemical treatment to treat our water, but according to mismanagement, most of my peers, they are having this outbreak of cholera. Now, the reason I put this is to show the importance of fresh drinking water, because the world has moved on from COVID-19, but us in the global south, we are facing problems of having fresh drinking water. Then forward osmosis, right? The word forward osmosis, we just use the word forward to differentiate it from the more common reverse osmosis. But this is basically the osmosis we learned in school, the movement of water from a region of higher water concentration to a region of a lower water concentration via a partially permeable membrane. But this forward osmosis has got two sections. The first one here, we've got our feed. It can either be brackish water or seawater, which has got these salts. Then we've got our partially permeable membrane. Now, the driving force for forward osmosis is an osmotic gradient. There's no pressure involved like reverse osmosis. So here, we've got our membrane. This is the membrane I used in my experiments. It's a commercial CTA, cellulose triacetate membrane. Both this was a self-assembled. I had to assemble this setup for my process. So initially, this draw solution, my draw solution is a higher osmotic pressure as compared to the feed solution, therefore forming an osmotic gradient. Therefore, the water will pass or permeate from the feed to the draw solution due to that osmotic pressure gradient. Then here the concentrated brine is collected. Then here the second step, that diluted draw solution is now to be regenerated so that we may collect the clean water and then it can be reused again. This is the process of forward osmosis. And these are the intrinsic properties of the membrane used. Then in this research, we're using organic draw solutions because most work has been done on inorganic draw solutions like sodium chloride, because Inorganic draw solutions, they've got low molecular weight, therefore they produce a higher osmotic pressure, although the reverse solute flask is a bit high. So in this research, we're trying to see if we can come up with novel organic draw solutions, either as mono or as combined with the combination of the two. So the first one, we're using cellulose derivative, either hydroxypropyl cellulose or sodium carboxymethyl cellulose, then as a binary mixture with the glycoether. And these are the osmotic pressures. I'll explain later these results in detail. Now, dynamic viscosity. Viscosity is very, very important in the draw solution because you have to pump the solutions in the system. So we're using an Anthony Per MCR 302 rheometer. These are for the pure cellulose derivative. You can see that by themselves, number one, because they are large, these are large molecules, they give low osmotic pressures, and also they are, if you look at a shear rate of 100, you can see that for this 2% hydroxypropyl cellulose, it has got high dynamic viscosity of nearly 180, which is not ideal. So by itself, it is not ideal for any desalination processes. But if we then add 7.5 molar glycoether, dilution effects, okay, we are reducing the viscosity. We can see at 25 degrees and at 30 degrees, right? The number before the cellulose is in weight percent. That means this is a binary solution of 0.5 weight percent hydroxypropyl cellulose derivative in 7.5 more glycoether. It's our binary solution. These are just the nomenclature. And as we can see here at 25 degrees, the dynamic viscosity are decreasing. Then at 30 degrees, as the temperature increases, the viscosity decreases. So by adding glycoether, we are reducing the dynamic viscosities, and in turn also we are increasing the osmotic pressures, making our solution ideal for desalination. This is stability diagram we found using thermogravimetric analysis, and we're using 5. This was the 5 we're using, binary solutions. This one was just a comparison because it doesn't contain the glycoether. And as you can see, apart from the comparison is binary solution, this one containing 1 weight percent sodium carboxymethyl cellulose in the 7.5 molar glycoether, that binary draw solution was the one which was most stable, and also further on it produced the better results compared to the others. Then osmotic pressure. The driving force of this process is the osmotic pressure difference. So we used a now freezing point depression osmometer to determine the osmotic pressures. As we can see, by itself, a cellulose derivative only had 26 osmolarity, which is nearly 0.665 bar, which is not any use in desalination. But if we use a glycoether by itself, this 7.5 molar, it produces very high osmotic pressures of nearly 70 bar. Then the binary, it produces the osmotic pressures of 34 bar. Now these osmotic pressures, they are ideal, but not for seawater desalination, because seawater is osmotic pressure of nearly 25, but for brackish water, these pressures will be sufficient. So this analysis is for desalination of brackish water, 1,000 parts per million sodium chloride solution. Then secondly, we're looking at, because we are combining, this is the FTIR of the standalone glycoether. Then this is the FTIR of the standalone sodium carboxymethyl cellulose. But the combined, as you can see the bands, this is just a combination of it. Nothing is being formed, so we can separate them using physical means. That was the purpose to determine the functional groups here, or using FTIR. These are the properties of the standalone cellulose derivative, then the glycoether, then our binary draw solution to see which conditions change: pH, electrical conductivity, TDS, salinity, and resistivity. And you can see by combining these, there's an effect on the final properties of our binary draw solution. Then this is the UV of our draw solutions, showing the absorbency. Right, then I have to explain something about forward osmosis. Right now, this process of forward osmosis has not been commercially utilized yet because there are many factors. The main one, there is no ideal draw solution. Like here, we're coming up with the novel draw solutions because there is no better draw solution. So in this research, because we're using new draw solutions, we also have to consider the compatibility with the forward osmosis membrane to see if there is no damages that is occurring. So initially, this is what we did it for only 1 week. I took my membranes into the different organic draw solutions. Then afterwards, I took fluorescent microscopy of this to see, to determine if there is any change in these 7 days. There was no actual, but we are going to do it for 30 days, and we are going to use scanning electron microscopy to see if there is any change on the surface morphology to determine the compatibility, and also try to use the UTM to determine the tensile strength after 30 days. Then this is the refractive index of before and after those 7 days. I took the draw solutions, then I determined their refractive index to see if there was any change in the optical properties, and also this is the UV after 7 days. Then the most important part, I should explain something. For this forward osmosis, there's what they call the solution diffusion model. From literature, this has been used intensively for inorganic draw solutions, but for organic draw solutions, there's limited work being done. Now, the solution diffusion model, it says that the diffusion of the movement of water is being caused by that osmotic gradient, which causes the diffusion to occur so that water may flow. And it says that the water flux is equal to this hydraulic permeability times the reflection coefficient times the change in the osmotic pressure. That means pi F minus pi D minus pi F. Now, this is the equation we used. Okay, this is the equation we used for modeling, and this is the equation we used to determine the salt flux. Then these are the results. Experimental flask is determined after every 10 seconds because from our setup we're doing balances. So after every 10 minutes, we noted down the change in the mass of the draw solution and the feed solution. So after every 10 minutes, we calculated our experimental flux in liters per meter squared. Then the modeled flask using those solution diffusion model. Then this one, the equation, the third equation, because there's something called concentration polarization. So this model, it included those, but in this equation, and in the blue one, it didn't. So you can see there's a gap here. And according to literature, they're saying that the solution diffusion model doesn't include the biofouling means. So they're attributing that change to those factors. Then for regeneration, first of all, we're going to try using molecular zeolites, 0.3 nanometers, 3A molecular sieves. This, and then to recover, we can use vacuum distillation. This is the first one, although it's a bit energy intensive. Or we can use membrane separation using a reverse osmosis. So that will be a hybrid FO-RO system. Then in conclusion, out of the initial 30 draw solutions, 11 had 12 had the osmotic pressures exceeding 25 bar. Then from those we chose 5. Then from those 5, the one with 1% sodium carboxymethyl cellulose combined with 7.5 mole of the glycol ether is recommended for further use. Thank you.
Any questions, please, everybody?
What is the durability of that membrane?
What is?
How durable is that membrane?
In fact, this membrane, it was used by people in 2015, and I'm using it right now, so it can be used for many years.
There is no need of any regeneration.
For that membrane, I can. Okay. After using it, I can, because of concentration polarization effects, I can clean it by soaking it, then then drying it. Yes, manually. I had to, because it's a self-assembled system. So after every run, I had to remove it, clean it, put it in water, dry it, restart several times. But I can use it over and over, although the performance reduces as the.
But what about the costing? Is it cheaper than RO membrane or what?
It's not cheaper, it's expensive because this is specialized. It's an asymmetric membrane. It has got an active layer and a porous layer. So this is ideal for forward osmosis. It's expensive, but you have to use it many times.
What benefit to use? What benefit to use? This is expensive.
The membrane. It's tailor-made for forward osmosis. So currently, most researchers right now in this field, they are not focused on this forward osmosis. They are focused on the making of the membranes. If you see people doing their researches, they are trying to make more cost-effective but better membranes. Those are studies that are also occurring. So as I said, this process of forward osmosis, it needs collective research for it to be utilized, so to avoid the scarcity of water by 2040. Yes, sir.
What is the thickness and porosity of the membrane?
Right. Sorry. Right. The porosity, these are the structural parameter is 655. As we know that we determine the structural parameter by the thickness and also by the porosity. These are the properties. So the porosity is this one, this value. And these are the tutorosity and the thickness. These are the intrinsic properties of the membrane used.
I think you have used a flat sheet membrane.
Yes.
Have you tried for that circular one?
According to this setup is self-assembled setup. So what I did, I had to harvest from that big setup and then to cut, because the active area was only 64 millimeters of this setup. So according to this setup, I had to use that flat sheet. But
it was a batch kind of system, or it was a flow system that you are showing it over here?
Sorry.
For this particular experiment?
These are the feed solutions, so I had to send them the feed, then also the draw.
This is system or control system?
No, batch system. After every run, I had to take results, then redo again.
So how you were measuring the flux part?
After it was 2 hours. The time of the experiment was 2 hours. So after every 10 minutes here, I was taking the readings. The change in the gain in the draw solution or the loss in the feed solution, and I was taking the value. Then the experimental flux now, the change in mass over the area times time in hours, in liters per meter squared. That was the experimental.
Did you find any difference between the two readings, one on the feed side, one on the strip side? Or it was exactly matching?
No, it was not exactly matching. So I made calculations using the gain in the draw solution.
It was
yeah, because
they were equal, or there was some difference?
No, there was some slight difference because the accuracy of these, they are not the same accuracy. So I was focusing on the readings from the draw solution side, the gain in the draw solution.
So you have considered only gain and not the loss part over here?
Unfortunately, yes.
Okay, thank you. It was a nice business.
Okay, thank you.
For the next presentation, I call Ms. Jigyasa Pathak for her presentation.
Good afternoon, everyone. My name is Jigyasa Pathak and I'm doing my PhD research work under the supervision of Dr. Poonam Singh at Delhi Technological University, Delhi. My presentation includes my work on the fissile synthesis of organo-modified layered ternary metal hydroxide for wastewater treatment. The contents of my presentation include the introduction about layered ternary metal hydroxides, followed by the need for development of LTMH, the objectives devised and the synthesis and characterization, followed by adsorption studies of the material, the conclusion devised, drawn and the acknowledgement. So talking about layered ternary metal hydroxides, these are 2D network lamellar materials and they comprise of positively charged edge-shared octahedral coordinated metal hydroxide layers that are sandwiched by charge compensated interlaid anions and water molecules. Their structure is related to the brucite structure, which contains MgOH whole twice octahedra, while in LTMH, the MOH whole twice layers are held together by van der Waals interactions. Now, there are a lot of methods for the synthesis of LTMH, including co-precipitation, hydrolysis, anion exchange, hydrothermal, electrochemical, and mechanochemical methods. And they have been used in a wide variety of applications, including water treatment, functional materials, catalysis, biomedical applications, and energy storage due to their unique properties, such as they have good anion exchange capacities and they possess high surface area, due to which they can be used in a variety of photocatalytic and adsorption applications. They consist of a homogeneous interdispersion of materials, which is typically difficult to obtain using conventional laboratory methods. They possess synergistic effects between constituent metals, and they are also highly thermally stable. So there is a urgent need for the development of LTMH, since the usage of extreme reaction conditions and toxic precursors serves as a hindrance in economic synthesis of LTMH via prevalent methods, while here we are using a fissile hydrolysis method which does not need high temperatures or pressures and uses fissile easily obtainable precursors. And additionally, there is limited literature available on synthesis and anion exchange of transition metals including zinc, copper and nickel. Furthermore, they possess excellent surface properties, but their utility in wastewater remediation has not been fully explored. Hence, the objectives of this work include the synthesis of zinc, copper, nickel layered ternary metal hydroxides, its characterization, and adsorption studies using the synthesized material. So, presenting the synthesis and characterization of zinc, copper, nickel LTMH, it was synthesized using a fissile hydrolysis method, wherein zinc, copper and nickel acetates were dissolved in a 1:1 ratio solution of ethylene glycol and water, and it was stirred in the oven for 60 minutes and then fully dried, after which we got a blue colored precipitate. While doing the characterization, first we did powder XRD, wherein we observed prominent and intense reflections at low 2 theta values, followed by low intensity peaks at higher 2 theta values, which are characteristic of turbostatic materials and suggest the formation of a layered structure. And the reflections appearing around 10 degrees, 21 degrees and 33 degrees were assigned HKL values of 003, 006 and 0012, considering the rhombohedral symmetry and lattice parameters ANC equal to 3.14 and 25.04 angstrom. From the FTI spectrum, we were able to deduce that ethylene glycol units were present in the interlayer region along with water molecules. Now, then we performed the adsorption studies, wherein first we studied the selective adsorption of material. The adsorbent was dispersed in a 1:1 solution of Congo red and rhodamine B dyes. From the visual examination, it was observed that after 30 minutes of stirring in dark condition, we obtained a pink solution which was different from the original pinkish red solution, which hinted that there was a selective adsorption of Congo red by synthesized material, and rhodamine B was left behind in this solution. So then removal efficiency towards anionic and cationic dyes was tested. Their adsorbent was dispersed in 20 ml solutions of 20 ppm Congo red, rhodamine B and methyl orange, and it was stirred in dark for 30 minutes. It was observed that the synthesized material exhibited best adsorption removal towards Congo red, which was found to be around 94%, followed by methyl orange, that was around 83%, and very negligible for rhodamine B, that was around 4%. This could be attributed to the preferential adsorption of anionic dyes over cationic dyes due to the electrostatic attraction and hydrogen bonding between the adsorbate and adsorbent. Then we studied the effect of contact time on uptake of Congo red by synthesized material, and rapid uptake of Congo red was observed in initial 50 minutes, which was around 90%, and it was observed that around the 30-minute mark, around 94% adsorbate was removed, after which it attained equilibrium. This could be attributed to the fact that initially, a lot of adsorption sites were present, due to which uptake was fast. With increasing time, adsorption sites got filled and adsorption got slower till it attained equilibrium. Hence, the conclusions drawn from the work are that ethylene glycol functionalized zinc, copper, nickel ternary metal hydroxide was successfully synthesized, and XRD results indicated formation of layered structure, while FTI spectrum suggests presence of ethylene glycol in interlayer region, and functionalized zinc, copper, nickel LTMH exhibited selective adsorption of anionic dyes over cationic, and percentage removal was found to be 94.3%, making it a good candidate for wastewater removal application. I would like to thank IPS Academy and organizing committee of International Conference on Emerging Techno-Economic Development for Social Environment, my supervisor Dr. Poonam Singh, and Delhi Technological University. Thank you.
Can you show that absorption?
This one?
That you mentioned, Okay, first. Next. Yeah, it goes to maximum to 94.6%.
So
What was the dosage of?
So dosage was 0.01 gram in 20 ml solution of 20 ppm.
Okay, so if you put more, it will go down 94.
Yeah.
Okay, yes, sir. So
If you go to the chromatographic column, so you will have.
yes, sir. Yes. So we are in the process of doing that work.
I want to stress that you have to say that
Okay.
and it is good to have 2-3 additions to showing what you have to.
Okay, sir.
It's very nice.
Okay. Thank you, sir.
There are 2-3 questions.
Yes, sir.
First, sir has rightly pointed out. You want to mention about the doses of adsorbent and the dyes you were taking.
Okay, sir.
Secondly, you have performed the experiment with 30 minutes.
Yes, sir.
And you're calculating the contact time after that or before that?
No, sir. 30-minute mark was the point where after which equilibrium has been reached. So at 30-minute mark, adsorption was found to be 94%, around 94%. After that, equilibrium has been reached. So there was no significant increase in the adsorption removal percentage.
That is what I'm saying. Why have you not taken 20 as a contact time? Because it is not showing much of the differences after 20 minutes.
So we want to see around 20, it was around 92%. So we wanted to see if there is significant, but after 30 minutes, there was only very slight difference between 94 and it was 94.3 or 94.4, like that. From 20 to 30, there is a difference of percentage, 2% or 3%. But
That's
after,
what I'm saying. If you talk in terms of industry,
yes, sir.
10 minutes of stirring time
Yes, sir.
is more costly.
Intensive, yes, sir. Yes, sir. But yes, sir.
Gone for 20 minutes instead of that.
Okay, sir.
Okay. Secondly, you have conducted the batch experiment
Yes, sir.
in a shaker
No, sir. On a stirrer.
on a stirrer.
Yes, sir.
Means you have done it at a room temperature.
Yes, sir.
Okay. Thank you.
Thank you, sir.
Now I call Ms. Ritu Sharma for her presentation.
Devendra Kumar and Professor Rajendra K. Gupta from Delhi Technological University. I am here to present my topic on isolation and characterization of a natural polysaccharide from kodo millet, a sustainable approach. So my presentation includes the introduction part and the current research. So I will start with the introduction. As my research is on underutilized cereals of India, so I would like to start with what are underutilized cereals and why they are called as underutilized cereals. So underutilized cereals are plant species that are grown for food, oil, fiber, fodder, and they have neglected due to their unrecognized nutritional values. Secondly, in India, at least more than 100 edible species of plants are being neglected or unexplored for their nutritional values. Now, the reason for their underutilization may be adaptation for the specific agroeconomical niches and marginal lands. Currently, it is less cultivated than other conventional crops, or maybe received little attention towards from the research. Now, natural polysaccharides, and the one which I am working on is known as mucilage. So mucilage is nothing but a water-soluble polysaccharide or a polymer which is edible and that constitute mainly carbohydrates and uranic acids units present in different parts of the plants like seeds, roots, stems, leaves, etc. The presence of mucilage on the seed coat prevents the plant from early seedling development, and they are like a jelly structure around fruit that maintain moisture level and prevent seed from completely drying out. Now, the millet which I am working on is kodo millet. Kodo millet belong to the family Poaceae, which is a grass family. Its botanical name is Paspalum scrobiculatum, and it is commonly known as rice grass. This is a picture of that kodo millet, and the second picture is when I soaked that millet in the water. Now, how I extracted the polysaccharide, the natural polysaccharide? First of all, I chose the plant part because mucilage or a natural polysaccharide can be extracted from different parts of plant. So first is the selection of the plant part. So I have selected the seed part of the plant. After that, the extraction. So extraction can be done by various methods, but I have chosen hot water extraction. Thirdly, after the extraction, we do the supernatant recovery, either by filtration or by centrifugation. After that, the polysaccharide solution which we obtain from the centrifugation can be directly used or can be lyophilized, which after lyophilization can be dried and used. Or thirdly, which is my specific area, the precipitation. So precipitation, we can precipitate the mucilage which is available in the whole solution by using acetone, ethanol, methanol or any kind of solvent. As mucilage is a water soluble and not acetone or other solvent soluble, so the mucilage part will be settled down and the other impurities will be in the supernatant. So after precipitation, we dried the precipitate and we got the purified mucilage. Now the purified mucilage we obtained after the extraction was done for the characterization. So in characterization, I have firstly done the FTIR just to know what are the functional groups are present in my polysaccharide. So from the FTIR spectrum, I got to know that the peaks which I am obtaining are specific for the polysaccharide mucilage. The broadband you can see around 3384 to 3275 centimeter inverse is typically for the presence of OH hydroxyl group. Thirdly, the mucilage show characteristic absorption around, you can see 1000 in the which is a particular peak for the region of carbohydrate. So this FTIR result shows that my mucilage firstly contain the hydroxyl group and it contains the fingerprint region of the carbohydrate, as the mucilage is mainly composed of carbohydrates. Secondly, I have done the XRD just to know whether my polysaccharide is crystalline in nature or amorphous in nature. So from the XRD, there was no, I got to know there was no sharp peaks. I was obtaining only the broad bands around the 15 degree to 25 degrees. So from the XRD, we got to know that the mucilage I obtained is amorphous in nature. Now, these are the applications of the polysaccharide which I extracted from the kodo millet. It can be used in the food industries, like for food packaging, edible coating, or in the pharmaceuticals for tablet binding, suspending agents or disintegrants, or in the cosmetic, agriculture and removal of contaminants from the water. So in my conclusion, the seeds of the kodo millets are the rich content of natural polysaccharide, which is mucilage. Secondly, good quality of kodo millet seeds mucilage can be effectively extracted by hot water extraction method with high yield. It is a cost-effective method as it consumes less volatile solvents, requires very less time for extraction, and gives the highest yield as compared to other methods reported in the literature. FTIR and XRD results indicated the successful extraction of the mucilage. These are the references. Now, I would like to thank IPS Academy, organizing committee, and my supervisor, Professor Devendra Kumar and Professor Rajendra Kumar Gupta, and Delhi Technological University. Thank you.
Any questions, please? Which method used for extraction?
Hot water extraction.
Is this a new method or it is already
No, it is already available.
So what new thing you have done over there?
Because nobody has done the extraction from the kodo millet, the polysaccharide from the kodo millet.
What are the different methods that are there for extraction of kodo millet?
Like you can do from the hot water or from the solvents directly, or with the cold water also.
If you are using the hot water, what were the earlier method that they used for in the
cold water extraction, hot water extraction, other solvents extractions?
So what the new things that you have done? That is why I'm asking.
My work is not on the method part, but from the compound which I am from extracting. So the compound is new, not the method.
Okay, the compound that you will be using, but you have not presented over here. Your most focus was the extraction part.
Yes.
But it is commonly available.
No, the method is commonly available, but the compound, the kodo millet, is new here, and the mucilage I am extracting from it is nobody has done that work.
Do you want to say it is a pioneer work of yours?
Yes.
How much amount you get after extraction?
How much amount? Approximately around 2 grams. From 50 grams. 50 grams. Yes, yes.
What is the temperature of oxygen?
Around 60 to 70 degrees Celsius.
How to maintain the temperature?
On hot plate. Yes.
So do you change the temperature?
No. Because after a certain temperature, the mucilage got decomposed. Yes, sir.
Have you checked the variation of temperature?
No. Yes, sir.
You mentioned lyophilization, drying method. Lyophilization, you mentioned that is really expensive also.
What are the different techniques of it? As the mucilage is water soluble. So after adding a thing which is not soluble in that mucilage, so it will settle down. Then I can
I call Ms. Jigyasa Pathak. I'm sorry for Ms. Priyanka for her presentation.
Good afternoon to all present here. I am Priyanka from DTU doing PhD under the supervision of Professor S.G. Warkar and Professor Anil Kumar. Today I am present my presentation entitled with Synthesis of Iron Oxide Incorporated Biocompatible Hydrogel Nanocomposite and its application in wastewater treatment. So here is the content of my presentation. Includes introduction, motivation and further objective methodology, conclusion and acknowledgement. So first we'll start with the background study. As we all know, treatment of water is a major concern nowadays because polluted water leading to serious health and environment threat to the ecosystem. And one of the major pollutant of water contamination is organic dye. Various methods are available for the wastewater treatment, includes adsorption, membrane filtration, photocatalysis, advanced oxidation process, etc. But we are focusing on adsorption because it is easier to use and more efficient and less expensive in nature. So a variety of adsorbents are also available in the market, but we are focusing on hydrogel because it received a lot of attention in wastewater research area because it is cost effective and it is easy to handle and it is environment friendly also. So moving towards introduction. Hydrogels are reported first by Witcher in 1960s. Basically, hydrogel is a type of gel having 3D crosslink network composed of hydrophilic polymer chain, and it has a property of water retention that is due to hydrophilic group. These hydrophilic group can be of amide, carboxylic, hydroxy, etc. And why the need of hydrogel and why these are used extensively? Because the synthesis part is easy and they can be modified by chemical method and they are obtained from the renewable sources, hence they are environment friendly also. Now moving towards the hydrogel composites. Hydrogel composites are the material which are made by reinforcement or by incorporating any filler into the hydrogel so that we can tune their property and we can enhance their application also. And the composite are designed by there are many various methods are available, like we can reinforce the hydrogel by any reinforcement so that mechanical strength can be enhanced and their property also improved, and they are biocompatible or bioactive in nature. So these are the properties of hydrogel. They have a property of high water content, their swelling ability, and they are biocompatible and responsive in nature. They are stable and versatile in nature. These are the classification of hydrogel. Various methods or schemes are available on the basis of which we can classify the hydrogel, like on the basis of composition, origin sources, cross-linking, ionic charge, and physical properties also. These are the method of synthesis of hydrogels. We can synthesize hydrogel by microwave irradiation, freeze thawing, electron beam irradiation, free radical polymerization, cross-linking, etc. These are the existing application of hydrogel. We can utilize hydrogel in agriculture, contact lenses, water remediation, food packaging, and biomedicines also. Now, our motivation for this work, we are synthesize a hydrogel, then utilize that hydrogel in the water treatment application, further check their efficiency and selectivity towards organic pollutant or any other pollutant which are available in the wastewater. And after that, we are trying to enhance that adsorption capacity of that particular hydrogel by reinforcing it with reinforcement. So these are the objective of my work. First the synthesis of guar gum, xanthan gum, polyacrylic hydrogel, then characterization of that particular hydrogel, then swelling study of synthesized hydrogel, and further check their application as an adsorbent for dye sequestration. So for that, first we have synthesized iron oxide nanoparticle by using the iron salt precursor, that is iron sulfate and iron chloride. Then stirring was maintained under the high temperature, and after that ammonia solution was added into it. Then color change was observed and temperature was maintained high, and after stirring of 1 hour, we'll get the precipitation, then filter out that particular solution and dried, then further calcined it, and the product was characterized. Then that characterized product was reinforced into the hydrogel. For that particular, the xanthan gum and guar gum was first dispersed in the solution in the water, then acrylic acid was added into it, then pH was neutralized, and then iron oxide nanoparticle was added into this. Then color change was observed from pale yellow to reddish. Then the solution was stirred for 1 hour and kept in water bath. After 1 hour, we got the product and we cut that into slices. Then it was dried and characterized. So here is the characterization. In the left one, this is the XID of iron nanoparticle, in which we obtained the peak near around 31 and 35, and it is similar to the alpha phase of iron nanoparticles. Then that particular, then here is the XID of loaded hydrogel, in which iron was loaded, and the control one in which iron was not loaded. So we got a hump that represent the amorphous nature of the polysaccharide, that is gum, and in the iron loaded hydrogel we got a comparatively sharp peak, that is due to the crystalline nature of iron. Further, the swelling study was performed for the hydrogel by using that particular formula, and it was observed that after 24 hours, the iron loaded hydrogel shows good swelling ability, that is around 10, that is 10 gram more than the control hydrogel. Then it was utilized in application of water remediation. For that particular, 20 ppm of dye solution was taken, and the hydrogel was and it was observed that the blank hydrogel shows 86 adsorption capacity, that is 86%, and after loading the efficiency was increases, that is 96%. By using that formula, we have calculated the adsorption capacity. Then effect of contact time. It was observed that as the time increases, percentage removal efficiency was increases, and it was observed that after 120 minutes there was not significant increase in the adsorption capacity was observed because the pores which are available are filled. So further, to conclude this work, guar gum and xanthan gum polyacrylic acid hydrogel was successfully synthesized by free radical polymerization method. Then the pre-synthesized iron oxide nanoparticle was successfully incorporated into the hydrogel matrix. Then it was characterized by XRD. Then swelling studies show that incorporation of iron oxide nanoparticle into the hydrogel matrix increases the adsorption capacity as well as the swelling ability. I would like to acknowledge IPS Academy, then organizing committee, my supervisor Professor S.G. Warkar and Professor Anil Kumar, and Delhi Technological University. Thank you.
Any questions, please?
Yes.
Yes.
What is the calcination temperature?
650.
650.
Yes.
Vary the calcination temperature?
What?
Vary the calcination temperature?
No, sir. Right now, I am working on this, but
Why you fix 650? On what basis?
in the literature, it is available like if we increase the temperature by variation in temperature, there is phase change in the nanoparticles, sir. So I'll try on 350 also, but here I have reported of 650.
What is the heating rate?
In normal oven, we have calcined. Yes.
What?
This is not centering. Yes.
Duration of calcination?
3 hours. 3 hours.
I think oven 650
Muffle furnace. Yes, sir. Yes. Yes, sir.
Yes, sir.
Increase.
Maybe interaction of iron, like iron has charge, so electrostatic interaction between the charges. Electrostatic interaction of iron to the hydrogen matrix, because hydrogen matrix has anionic nature. So plus charge and negative charge, so there will be electrostatic interaction. Yeah. No, sir, as the swelling increases, so absorption capacity may also increases. That's why we incorporate iron into this, so that we can increase the swelling ability and the absorption capacity also. Like I am working on the adsorption doses and concentration also, but this is the preliminary experiment.
Okay, so you are extracting water and you're leaving aside the time for
Yeah.
Yes.
Sorry, sir.
You have been spending on the time.
So for now, this was the last presentation. Now I request Dr. Bagdu Awalawa sir to felicitate Dr. Ashwini Rathod sir with a memento as a token of gratitude.